Good morning. My name is Ian Logan with 3C Ren in the County of Ventura. We are here for the role of building science in high performance buildings, also known as science in buildings and part 2 science and buildings. This is the first of our high performance fundamentals series, which will provide a bit more context to in the coming slides, but I will just walk you through some housekeeping and Zoom orientation while we're all getting settled here this morning. Next slide, please, Peter. So by now, I'm sure most people are feeling pretty comfortable on Zoom, but just a few PSAs before we get started. We ask that everybody remain on mute throughout the duration of the training. If you would like to verbally participate, we will either invite you to do so or please raise your hand in the participant section. More likely, we invite you to participate and ask questions through the chat box, which I will relay to Peter as they come up. So we'll try to get live answers to those questions, and then if time permits, we will have a Q&A at the end of the session. But at the moment, if you'd like to maybe introduce yourself, you're welcome to do that. Include your full name, profession, and maybe where you're tuning in from today. And then for attendance purposes, I don't see any phone numbers, which is great, but we like to keep it with first and last name just for attendance and our reporting. And then lastly, this class will be recorded for our on-demand page. So if you'd like to remain anonymous, just please keep your verbal participation to a minimum, and we shouldn't have any issues there. Next slide, please. So the Tri-County Regional Energy Network, we are also known as 3C Ren. We're a collaborative partnership between SLO, Santa Barbara, and Ventura counties meant to improve energy efficiency in the region. 3C Ren is funded by ratepayer dollars that we all pay into in our utility bills through the public goods charge. The benefit of being ratepayer funded is that there's no cost to those that we serve. And as a regional energy network, we're able to return these dollars back to our local economy. Next slide, please. So there are a few staff members on the training today. You'll recognize them with, a 3C Ren branded background. You're welcome to chat me or them directly if you're having any technical issues that we should try to resolve for you, or if you have any questions about 3C Ren and the general program. Next slide. We currently offer these 3 programs. We have the Energy Code Connect program, Home Energy Savings program, and the Building Performance Training program. Next slide. So Energy Code Connect serves all building professionals. We offer services for everyone from plans examiners and inspectors to architects and contractors for both residential and non-residential application. Under ECC, we offer 3 distinct services. We have the Energy Code Coach, which is a Title 24 consultation service. You're able to call or text the phone number on the screen here. You can also submit a claim on our website and expect a 24-hour response time for any Title 24 questions. We also offer trainings similar to what we're sitting in today, but with a focus on energy code comprehension, compliance, and enforcement. And then we offer quarterly regional forums that kind of offer a networking opportunity for our group of stakeholders. Next slide, please. Secondly, the Home Energy Savings Program is our most public-facing program. It serves households that are historically underserved with flexible energy upgrade options. There are simple upgrades available for free, and then discounted upgrades that provide greater savings, like heat pump water heaters, HVAC systems, Energy Star appliances, new insulation upgrades. The list goes on and on. I invite you to visit our website to view a more comprehensive list of the upgrades and incentive amounts. Next slide, please. So the Building Performance Training Program, also known as BPT, is the reason we're gathered here today. We offer trainings to architects, engineers, contractors, real estate professionals, and those looking to join the industry. We offer technical and soft skills trainings related to building science principles and systems for high performance buildings. The goal of our program is to bring industry recognized certification and training providers to the Central Coast that will help advance people wherever they may be at in their career. Next slide. With that, I am going to hand it off to Anna Minster to introduce the designated high performance fundamentals series that we have been working very hard on over the last year. But yes, I will let Anne introduce the series and kind of ground us on the background and who this series is intended for. And the floor is yours.
Thank you, Ian. Wonderful. Well, we're quite excited to be here with you all launching this program. We recognize that it's going to be sort of a slow launch because it is really quite new for 3C Ren and based on a lot of background work, as Ian mentioned. So,
and you've muted yourself.
Oops.
Excellent.
Yeah, hit the wrong key on the keyboard. Anyway, Pete, can we go to the next slide? So background here, part of this is we did a whole bunch of research over the past year. And first of all, obviously, we've got a definition of high performance. What are we talking about? Essentially, this is above code performance and looking at all aspects of how we get to that performance. It's not just design, but how the buildings are built and put into operation. And one of the things that we learned through this research process is that it's still a relatively niche, or as some people like to say, niche function within the building industry. But those firms who are doing high performance work find that they have no shortage of work ever, regardless of the state of the economy at any given moment. And they also have a tremendously difficult time hiring people who have the basic qualifications that they're looking for in new hirees. And either folks who've been in the industry for a while are very busy and very content doing things the way they have always done them, or they're people coming in new and there's really no avenue for them to acquire the basic knowledge they're after. Next slide, please. So what we're trying to do here is do two things. Both create an opportunity for those who are coming in and have an interest in going after these competitive jobs where there's, again, fewer. This is not every company that's looking to hire people with these skills, but they are very selective companies who are really targeting high bar performance. And then secondly, for those who are already in the industry, perhaps backfilling some knowledge or refreshing knowledge that will get them in a better position to also target these high performance jobs. Next. So the content was developed in consultation with many, many experts in high performance building businesses across a pretty wide range of occupations, from tradespeople, general contractors, consultants, architects, engineers. So we talked to a lot of people to make sure we were looking through all the appropriate lenses and found a remarkably common desire for the base level knowledge that they were seeking in the new hires. And that base level knowledge is fundamental building science and the practices to put into action those principles and distinguish them from the conventional practitioners within the field. Next slide. So we've got a lineup of 6 classes in sort of the first tranche, if you will, of classes. We certainly have a longer list of things that we believe are ultimately needed, but these are the ones that rose to the top for the first go. And as you can see, there are 3 of those classes that are on the calendar already, and 3 more coming in the fall. And I'll also note that the first 3 are a bit scrambled in calendar order. Don't be too confused by that. We felt that the rate, the sequence of offering classes 1 and 2 were not so critical, in as much as class 1 is not highly technical, so it can be inserted after class 2, which Peter is teaching today and on Thursday. I had to think about what day of the week it is right now. And then Rick Chitwood is teaching high performance buildings and careers in June, which will give a bit more of the background for what this opportunity is and what it means to be differentiated from the mainstream industry. Next slide. So in the future, we are hoping to roll out quite a bit more of the high performance fundamentals program, going beyond just this first series of lecture classes. We hope to offer a certificate of completion to those who take all 6 lectures, and then ultimately to have field-based classes that will complement the lecture classes. So if you attend Pete's classes today, there will be lecture classes, or sorry, field-based classes to complement those and the other classes that follow in this lecture series. And then also later on to have more of a peer learning network and or mentorship opportunities to continue that learning and deepen it as folks get into the field and begin to try and put these principles into practice. Next slide. So, and actually before we do this, before we launch with Pete, I'll say a few words about him, and then Ian has a poll also, so we can find out a bit more about who is with us today. We know many of you are known suspects, but we still want to get that for Peter. And so Pete and I have worked together, known each other, and become very close friends over the better part of a quarter century at this point. And so I think have a very high level of mutual regard. And so even though Peter's in Vermont, I'm in California, we have crossed paths really so often, and with I think a lot of common interest over the years, that he was really the logical person to pick for this. His background includes being a high school teacher of science, working with youth in wilderness and teaching science as well as life skills, and then going on to work for the National Association of Home Builders, for Building Science Corporation, which is probably the most highly regarded building science firm in North America. And there are so many other credits to his life story. I've asked him to give you his version of his life story, because I think it's important that you all have a sense of, well, okay, so these people are high performance practitioners. What in the heck does that mean? And how did they get there? So with that, we'll, I guess, keep the poll up for another couple minutes or so. I think you're able to drag it from the front of your screen so you will not miss out on Peter's slides. And over to you, Pete.
Thanks
Break
much,
leg.
Ann. Yeah. So as Ann mentioned, I taught high school. I taught physical science, biology, and chemistry, which we'll come back to a little bit later. But while I was doing that in the summers, I had a couple of brothers who ran a building company. And the interesting thing about that company is that each of us had a master's degree in something. But when it came to how we thought about buildings and worked on them, it all came back to Joe Prue. Joe Prue was my oldest brother's father-in-law, and Joe Prue was a 7th generation French Canadian framer. And he was about 130 pounds with his tool belt on. But you did things Joe Prue's way on the job site, or you didn't do it at all. And so my first experience with building was just learning what was in other people's blood. You know, this Joe felt that he was intimately genetically wired to be a carpenter and to build buildings, particularly homes. But then, you know, I ended up with a health problem, went back to school, and I ended up at the National Association of Home Builders Research Center, and I had to relearn all again how I thought buildings worked. And then because of a change in family circumstances, I switched over to Building Green, and that's a small consulting firm in Vermont, And again, I relearned how I thought about buildings. And then I went from there to Building Science Corporation with Joe Stiebrick and Betsy Pettit in Westford, Massachusetts. And I had to like throw out everything I had learned and start over once again to understand how buildings work. So it's been a long journey. It probably is for most of us in this industry. But this program is about how buildings work. And I think one of the curious things about this is that many of us who know how to design or specify or construct buildings, we don't necessarily know how they work, because how they work is proven over time, and it's done by the homeowners or the occupants. So, you know, we have to, as we design, specify, and construct, we have to understand that these buildings have a life that goes way past our involvement with it. And that's the important thing to keep in mind, and what I've had to sort of relearn over time. So I'm going to try to move the poll because it's right in the middle of my screen. I guess I'm just going to end the poll. I'm looking here. We've got contractors, architects, quite a few consultants. Okay. And I guess I have to stop sharing that. Is that how that works?
Not your screen, just the poll.
No, I don't want to leave the meeting.
No.
Um,
I'll stop sharing the poll, and you're welcome to pull up your slides again.
Sorry,
Okay.
did you run through the other 3 questions though, Pete?
There were more questions?
Yeah, there's 4 questions. So just so you can see the distribution, how many years in the building industry. Let's see, we've got 22 folks who have less than 5 years, 2 who have 5 to 10, and the remainder have more than 10 years in the building industry. If in the building industry, what is your position in the organization? Similar split, 2 at entry level, 1 at mid-level, 1 supervisory, and 5 executive or owner. That's great, because we want to hear from you at the end of class about your thoughts about who within your organization might take these classes. So excited to see that. And then what prompted you to take the class? 4, say, desire for career advancement or enrichment, and 5, personal curiosity. You're just snooping. That's okay. We love that. All right. Thank you. Carry on.
Yeah, I lost my screen here, so I'm trying to head back. Okay, now we're back to the slideshow. So I mentioned it's about how buildings work, and you know, the first thing about my work is that's a little bit peculiar is quite a few of the things that we know that we think we understand about how buildings work have not necessarily been sort of field tested. So I do a lot of work trying to figure out how buildings actually perform. Here I'm working with a local high performance building professionals group, and we're trying to figure out if we can really understand soffit to ridge flow. So I've got my theatrical fogger, I've got infrared lamps, and we're watching what happens to the fog as it moves up in the space between what would be the, you know, the roof deck and the ventilated space between that and the roof cladding. And I've done a ton of videos on this. There's a lot of content on Green Building Advisor about the work I've done, but you should understand that this work that is both, you know, this is benchtop sort of, or inside a building, but I also carry it into the field. But I call it wing nut testing because it's really not codified, it's not standardized, but I've learned a lot about how buildings work over the years by actually doing field testing with materials that we depend on, or principles that we depend on a lot to understand how buildings work. So I hope all of you will aspire to be wing nuts as well. This class is 2 parts, an hour and a half each. And by the way, Ian's going to monitor questions. We're going to try to take them as we go. I can stay about 15 minutes or so after the end, and we can cover questions then as well. But we have 2 1.5-hour sessions, and I broke it into this idea of, we're going to talk about science and buildings and sort of their relationship on a sort of a basic science level. But then part 2, which you come back for hopefully on Thursday, is, all right, let's take that science, which we talked about in part 1, and translate it into buildings. So this today is not quite as hands-on or as directly applied as part 2 will be, but we're going to lay the groundwork to show how strong the relationship is between building performance and basic science. There'll be homework in between the 2 sessions. And then hopefully we'll have time for discussion about what we've learned, and you'll see from the homework exercise that that's going to be discussion based as well. So we have trouble with terminology in our industry. There's green building, there's sustainable building, there's high performance building. And when it gets right down to it, particularly for our clients, they just want to know what makes some homes work better than others. So I chose 2 homes. These are within 4 houses of each other. And the one on the left is a net zero building, and the one on the right is just a run-of-the-mill home. They look a lot the same. It's really hard to tell when the environmental footprint of a building is significantly less or when it might be net zero. We're going to come back to these 2 examples in part 2, but how do we explain to people that 2 buildings or 2 homes can look so much alike, and yet the impact of their performance and how well they serve the occupants or the owners can be completely different as well? And by the way, most lay people are terrified of their homes, in the sense that there's a lot of jargon with the industry that they don't understand the terminology that we use. And so they tend to take this very black box approach to how their buildings work. And that's not, of course, how they should view their homes. They should view their homes like they view their vehicles or their laptops or their phones, which is, oh, this is a functional item that I bought. I want to understand how it works. And so one of the translations we have to make as we talk about high performance building is we have to make people understand that buildings are not scary, and they are the most expensive, the longest lived high performance item they're ever going to purchase or own. So what does better mean? How do we create a definition for what high performance is or what better performance is? So I like to think of it this way, and this is just my definition. I think each building professional needs to not only have their own definition, but also work with their clients to make sure that you have the same definition of what high performance or better means. So I think of homes as efficient. That means that they efficiently use energy, water, and materials. Now, the materials is really from cradle to gate, but that's all efficiency. We can make sure that the building in operation uses energy and water well. And then in terms of materials, when we design and spec the buildings, they should be safe. A big part of the building code is about safety. I've highlighted indoor air quality here because fire is part of the code. Indoor air quality is gaining traction as part of the code, performance codes across the US, including Title 24. And then durability is a huge part of this. If I make a building that lasts 3 times as long, I've cut its environmental impact by 1/3, at least in terms of the structure, right? Because if I have a building that lasts 1/3 as long, I have to build 2 more, and that's a huge impact in the embodied impact of that building. So durability is a huge issue when it comes to high performance. Also, it should be built to serve over time. So designing buildings that can be easily changed in terms of their configuration or sort of outfitting becomes important. And then resilience, of course, is when we have these buildings that in addition to being durable under normal circumstances, they become durable or keep their service under very stressful conditions. And buildings have to be, in terms of better, easy on the occupants, the community, and the planet. And those are three very different levels. But if we leave one of these out, we're not going to make the impact that we want on terms of low impact buildings. So I like to think of this as the electric slide, because in order for us to make homes that work better for the planet, we are going to have to electrify them, because that's the only way that we can really have a control over satisfying all the loads. And we'll come back to this in part 2, all the loads created by heating, cooling, appliances, lighting, plug load, domestic hot water. We have to electrify all of them, because that's the best way we can move to decarbonizing the way that the buildings work and decrease their impact on climate change. And I've got a picture of the same house, which we'll return to in part 2, when we sort of do more, after we've done the groundwork, we move on to how does this all translate into the way that buildings actually work. So there's just 3 things. We're going to talk a little bit about physical science and how it makes its impact on how buildings work. Then we're going to do a bit of chemistry and then a bit of biology. And you can tell, I mean, I was a high school teacher. I never connected when I was a high school teacher how physical science, chemistry, and biology could be applied to buildings. But I found myself over the next 25 years after leaving high school teaching that the background I had in the physical sciences, and actually we all have this, right? If you're a high school graduate, you have some background in physical science, but chemistry and biology, but how does that translate into buildings? And remember, because I did things the way Joe Prue taught me, initially, I wasn't making these connections between scientific principles and making homes work better, but that's what we're going to be talking about. So we're going to start with an example from physics, which is the relationship in buildings between wind and pressure. Now, wind is a force. Pressure is a force per square area or per unit. And so they're not the same. And so when we look at wind speeds, 20 miles per hour actually translates into a pressure measurement. And this is the pressure of a building. That 20-mile-per-hour wind can create a pressure within the vessel, which is the pressure vessel of the building, of 50 pascals. A 25-mile-per-hour wind, and remember, these are sort of general numbers, but is 75 pascals. In order to get up to the most powerful hurricane we've ever experienced, now we're talking about 6,400 pascals. Well, turns out 6,400 is right around 1 pound per square inch. And so that's a force. But when we talk about these different pressures, how do we translate that into what actually happens on buildings? So I'm going to stop the share because I want to go to a real quick video. See if I can do this by jumping out of the slideshow here. And I want to do another share. And it's going to be, let's see if I can find this video. Oh, I think it's that one. Sorry for the delay here. I'm actually going to jump out of the. Sorry, I'm having trouble finding my screen here, but I will shortly. Oh, goodness gracious, where is my slide for?
Peter, you can also pull up the browser screen, the YouTube page, and then when you go to share screen, it should show up as an option.
Yeah, what's weird is I'm having trouble locating that one, but hold on while I. Okay, let's see if we can It's weird. I don't see it among my choices for share. How is that possible?
There we go.
Okay, now I just have to be able to. So this is the Institute for Business, Home, and Safety. And I just want to show you this video briefly. You can see and hear this?
The audio is very quiet.
Is to deliver top-tier science and translate it into action. To build better homes, stronger businesses, and thriving communities that can stand up to disasters like hurricanes, damaging hailstorms, tornadoes, and wildfire. We are an independent, nonprofit scientific research and communications organization dedicated to exploring the intersection of weather and the built environment. A unique research center located in South Carolina enables us to conduct rigorous, realistic, full-scale testing of homes, commercial structures, and building components against wind, wind-driven rain, hail, and wildfire. Our world-class science turns into actionable solutions for the insurance industry, policymakers, building professionals, and the public. The work we do improves design and construction across the U.S. through better building codes and more realistic test standards. By building better, stronger homes and businesses, we reduce the disruption and displacement that all too often follows catastrophic events, and we accelerate economic recovery. Mother Nature is not letting up. We can narrow the impact of natural hazards on communities. And together, we write the story we tell after the storm, from one of despair to one of hope.
So I just wanted to show you that video because, well, let me see if I can stop the video. And now I'm going to go back and share my screen again.
Peter, I'm gonna put the link to the video in the chat as well, just because the audio was a little quiet for people.
Great. Excellent. Thank you. So I think we were here, and now we should be looking at the presenter view again.
Yep.
So what's interesting about the work of the Institute for Business, Home, and Safety is that they're looking at making better homes, higher performance homes, but related to really stressful events, you know, floods, hurricanes, tornadoes, wildfire, all of which have been aggravated by climate change. So when we look at this relationship, you know, the science, which is basic physics, translating wind speed to building pressures, is a big part of, you know, science and buildings. It's an example with physical science. So what about a quick example of how chemistry makes its way into buildings? Well, almost every air control layer, water resistive barrier connected to flashings, we now are incredibly dependent on what are called pressure sensitive adhesive tapes, PSA tapes. And the chemistry of them is really kind of fascinating because the polymer that is the adhesive is a huge organic polymer that needs to be quote unquote wetted. And the way it gets wetted is you put pressure on it. So when you exert that pressure, the energy of that pressure liquefies that adhesive. So you can see here in the middle that when you exert the pressure, you get the polymers to go in and grab and electrostatically bond to the substrate. But then there's a dwell time, which means that to get the best contact, you have to let that system rest, usually for 24 hours, to complete the bonding. So what does this have to do with building? Well, if two of the most important control layers that we have in building are depending upon this really complex polymer chemistry, we have to have a basic understanding of the chemistry involved, because it's going to make our application of that science much more meaningful, much more durable, much more better service life over time. And finally, when we talk about biology, of course, the first thing that always comes to mind for me is mold. Mold is fascinating because it's everywhere all the time. Mold has been around a lot longer than we have. We had to learn to live with mold. Mold didn't have to learn to live with us. And so the relationship between science and buildings, when it comes to moisture and energy, mold is one of our scariest, and also most prominent expressions of biology in buildings. You can see here that mold can grow on the outside of a building. This is mold in a basement or a crawl space. This is mold in an attic. And so we have to include biology in our understanding of how to protect the building and how to protect the occupants when it comes to things like biological contaminants or critters, pathogens, living pathogens. So that's just 3 quick examples. You're going to see from the homework at the end of this session that what I'm hoping is that you'll think of your own examples like, yeah, I've always wondered what the relationship is between this scientific principle and how my building or my home works. So as we're going through here, be thinking about questions that you come up with about how basic science expresses itself in buildings. So today, it's going to be pretty simple. We're going to look at 3 basic questions. How does heat get around? How does water get around? And then how are the 2 related? And you could say, yeah, well, this Vermont guy, I'm sure he's got to deal with a lot of water. There is no climate where we don't have to honor this relationship. There is no climate where this doesn't become really important in terms of making it safe for occupants and making it durable. So we're going to take a look at the science behind how these 3 questions can be answered. So how does heat get around is the first one. So there are only 3 ways that heat can transfer here on Earth. And the first one is radiant heat transfer. And radiant heat transfer is driven by surface temperature differences. So the sun, which is super hot, 10,000s of degrees Celsius on the surface of the sun. It travels 93 million miles through outer space to hit the Earth. And the scientific principle is that if one surface that can see another surface is hotter, there will be photon exchange proportional to the temperature difference. So it means that if the sun is very, very hot and the Earth is much cooler, there is exchange between these 2 surfaces, but the net transfer is heavily favoring electromagnetic energy coming from the sun to the Earth. So we call that radiation. It's actually electromagnetic waves. They always move from high to low through empty space. So in order to get this transfer, you have to have an empty space, because that's how electromagnetic waves move, and there has to be a temperature difference. And once that electromagnetic energy strikes an object, the energy can be transmitted, reflected, or absorbed depending upon the properties of the surface. We're going to come back to that in a little bit. So for some of you, this may be like, oh yeah, I do remember this from physical science, but it's important how it applies to buildings. So 3 forms of heat transfer. The second one is conduction. So conductive heat transfer is driven by temperature differences within solids. So we have here in a building a wall. If it's warmer inside than outside, then there is movement of energy by conduction moving through those solid materials. And conduction is just direct transfer of kinetic energy. So the warmer brick molecules here vibrate in place faster, and that means that to go from high to low, from lots of kinetic movement to less kinetic movement, we have this conductive flow of energy through the system from high to low, and it's always in solids. Anytime we get heat transfer through a solid, we're looking at conductive heat transfer, and it's pretty quick. Now, it's not nearly as quick as the speed of light, which is how radiant energy transfers, but it is pretty quick. And it depends upon how the kinetic energy gets transferred through different solids that will determine how fast that energy moves. So we're almost done. The third form of heat transfer is convective, and that's driven by temperature differences in fluids. And we have, fluids are liquids and gases. Because solids, the molecules are locked into a matrix or a crystal, but when we have fluids, gases and liquids, they're free to move about. Certainly gases move around more freely than fluids, than liquids. And you can see in this example, we have air, which is cooler, moving in the space between the radiator and the wall, and it gets warmed. And because warm air is less dense than cold air, the molecules fight to be further apart, and they can become further apart because air density can change relatively easy because there's lots of empty space in between. But interestingly, if this radiator is a hydronic radiator, there's another convective loop, right? There's this fluid, which is warm, is being moved through the radiator. So we actually have two convective loops. We have a convective loop in the fluid, the liquid, a type of fluid in the radiator, but then the air is another type of fluid. It's a gas that can move through. And so it's a temperature gradient, just like with heat transfer. It's the same kinetic transfer of energy. It just so happens that they're not bound into a crystal matrix structure. Now, one of the things that's important as a little side note to keep track of here is that we often hear the expression heat rises. Heat does not rise. Heat moves by gradient. So if there's a warmer surface over top of a cooler surface, the heat transfer by radiation is going to be down. It doesn't care what direction it goes. When we talk about hot air or a fluid, yes, fluids, gases and liquids move from low to high because of density differences, but that's not the only type of heat transfer where we have fluids rising is convective loops. And you're not going to believe this, but I was on a project where a mechanical engineer was talking about why we didn't need insulation between the ground and the slab above. And I said, well, why don't you? He said, well, heat rises. And that was a little dumbfounding because heat doesn't rise, hot air rises. The heat was moving down through the slab just as readily as it was moving up. So these physical expressions of how heat moves are fundamental, and they have to guide all of our understanding of how buildings work. So this is a picture of a wood stove, of course, and it's kind of an expression of all three types of heat transfer. When I was going through my slides this morning, I thought, yeah, they're going to think, why the heck is this guy from Vermont showing a wood stove when we're supposed to be talking about reducing climate change by not using fossil fuels? And what's kind of funny about this is that, believe it or not, Efficiency Vermont, which is leading the charge to electrify Vermont, promotes the use of heat pumps with wood stoves. And the important thing is that when it gets super cold and the heat pumps can't deliver, the heat pump cycle of a mechanical advantage, they actually want people to run their wood stoves as a way of overcoming the inefficiency of the heat pump when it's super cold here in Vermont. Or the wood stove becomes the backup heat if we get an electrical outage. Now you could say, yeah, but we're burning stuff. Well, wood's not a fossil fuel, right? And it can be sustainably managed. So if Vermont is more than 3/4 trees, and we can figure out how to manage them sustainably, then there is a connection between our version of electrification that's based on climate. So the principles are the same from Vermont to California, but the expression might be different because of local circumstances or just how different your environment is. So our solutions can be climate tuned. And, you know, how are the three types of heat transfer happening here? Well, if this is a super hot surface and the metal's cold, the radiation will be directed from the surface of the wood stove to the metal. But of course, the metal is reflective. So, you know, it's reflecting the radiant energy back into the room. Here we have a different setup, a completely different background, but the same wood stove. And so when we think about how energy is being transferred for this setup to this setup, well, there's radiation happening from the wood stove to the stone wall, but what happens to that radiant heat transfer is very different than what's happening here. So we have convective heat transfer because the cool air comes and is heated around the wood stove. We don't have much conduction going on, and hopefully we can teach small children not to deploy conduction when there's an acting wood stove. But my point is that regardless of the type of heat we're working with, all three forms of heat transfer are always present. Certainly if these stones here, which have high mass, heat up and they're in continuous contact with the wall behind, we're going to have conductive heat transfer. Now, if you go back to this surround that protects the wood stove, kind of looks to me like there's a gap between the metal surround and this. We're trying to produce a non-conductive transfer here between the metal and the wood stove. But to completely understand the situation, we have to go back and spend a little bit more time with radiation. So remember when I talked about radiation, there were three outcomes. If this radiant electromagnetic wave comes and strikes this surface, there are three things that can happen. It can be transmitted through, right? Basically, we're talking about if this were glass. The radiation can be reflected, right? There's a whole bunch of materials. Certainly the shiny metal was reflecting. And then the third thing is it can be absorbed. And each of these is critical to understanding how energy moves through buildings. Once the electromagnetic radiant energy is in the material, well, this surface can re-emit the energy. So if this column here is heated by electromagnetic energy and this one is not, and the surface of this one is higher than this one, it's going to emit from here to here. The same could be true here. If this surface is cooler and I heat this entire mass, then every surface emits energy based on the surface temperature difference between any surface that it sees. There's no easy way to say this. The emissivity of materials, and this is really important in building materials, it's just plain weird. And here's why. Once the energy is absorbed, how readily that energy is re-emitted as radiation from the surface material, that's called its emissivity. Shiny, polished materials are very poor emitters. Rough, dull surfaces are very good emitters. So that means that metal, just because of the atomic alignment at the atomic level of the material, completely changes the performance of this material in terms of what happens to the energy that's absorbed into the material. Is it readily re-emitted or is it reluctantly emitted? And all I can tell you about this is, for those of you who maybe had to suffer through physical chemistry in college, is that the science behind this is incredibly complex. It has to do with electrical electron spin. It's an atomic level expression of physics. And the way that we evaluate this emissivity is that if a material doesn't emit any of the energy that it absorbs, it's given a number of 0. And if it emits all of the energy that it's containing, emits it at its surface, we give it a value of 1, and then everything else is somewhere in between. So how does this translate on a Tuesday into how buildings work? Well, here are some common building materials, and you can see that here's how readily they absorb electromagnetic energy. And you can see stucco doesn't absorb all that much. Red brick does. Look at polished aluminum. Wow, only 10 to 30% of the solar energy that hits that polished aluminum gets absorbed. What happens to the rest of it? Gets reflected, right? There's only 3 things that can happen. It gets transmitted. Well, it's not going to get transmitted through a brick or a polished aluminum surface. It can be reflected, or it can be reflected, absorbed, or transmitted. So look what happens here. The red brick absorbs quite a bit, but look at its emissivity. Of the energy that it absorbs, 90% is readily re-emitted at the surface. Look at aluminum. It only absorbed 10 to 30%, but it is very reluctant to give it up. It's shiny metal. So what this means is that if you had a white Camaro with its hood in the sun, it would absorb way more of the solar energy than a DeLorean, right? But the Camaro is going to, of the energy it absorbs, re-emit 90% of it. The polished aluminum, it absorbed less, but it gives up very little. The surface temperature of the DeLorean would be way higher than the surface temperature of the white metal Camaro. So how is this important in buildings? We've got to understand all forms of heat transfer, and particularly what happens when we have radiant expression of energy at surfaces. So I'm going back to the wood stove, because the way that this surround handles energy, if it's a shiny metal and this wood stove is radiating lots of energy, a very, very large proportion of that energy gets reflected as radiant energy into the room. It makes us warmer. Why is there an air gap behind this? Because it's shiny metal on the backside. As the surface of this metal goes up because of the energy that it is absorbing, it very reluctantly emits to the backside. So there's 2 things going on here related to radiation. The shiny metal reflects most of the radiant energy, and of the energy it absorbs, on the backside, it very reluctantly radiates energy to the wall behind it. That is very different than the way that this surround is working. This radiant energy, very high portions are being absorbed, but very high portions are also being re-emitted because the emissivity of rough, dull surfaces is very high. So just a really simple example of how understanding the really basic physics of heat transfer leads us to different solutions in terms of protecting assemblies, in terms of combustibility, but also in terms of the ultimate goal of this wood stove, which is to warm the occupants in the building. One more thing about heat transfer, which is the most complicated heat transfer element in any building are the windows, the glazing. You can see here that we have all 3 forms of heat transfer happening at the same time. We've got conduction from glass to spacer to glass. I'm sorry, that's up here. We've got one convective loop on the outside of the building. We've got another convective loop between the 2 sealed panes of glass. Then we have a third convective loop that's happening in the room inside here. And you can see, because of the arrows here, all the heat loss, whether it's conduction or radiation or convection, this has got to be warm inside, cold outside, and all of the heat flows are from the inside of the building to the outside. So it's probably nighttime in a cold climate. But windows are incredibly technologically complicated because all three forms of heat transfer have a huge impact on the energy performance of glazing. And it's also among the most dynamic because as soon as the sun comes out, even on a cold day, the relationship between convection, conduction, and radiation changes dramatically. That creates incredible stress to the insulated glazing unit. It means that we have, over a very short distance, we have huge temperature extremes possible. So when we talk about building high performance buildings, the amount and the type of glazing becomes really important, regardless of climate, but certainly very important in all of California's climate zones, but certainly all the climate zones for the 3-county region. The other thing that's complicated about windows is that we put on what are called low E coatings. And you've probably all heard of a low E window. The E stands for emissivity. So how does that work? Well, it turns out that if we put a low E coating, which are very, very tiny flecks of shiny metal, silver, tin, it turns out that the energy coming from the sun is very shortwave infrared, and it readily passes through the glazing unit. So you can see here, shortwave radiation transmitted through the glass. Now, when that energy hits like the couch or the floor, it warms the surface of the couch or the floor. And if it warms the surface of the couch or the floor above the surface temperature of this glass, then long wave radiation takes place. Why is it long wave radiation? You only get shortwave radiation from incredibly high temperature objects like the sun. If the temperature of this couch or floor is only 100 degrees Fahrenheit, then it re-emits the energy as long wave infrared. And look what happens. The low E coating reflects that. So low E is always about whether the energy coming electromagnetically is passing through, being absorbed, or being reflected. We get to do all kinds of cool things with glass because of this phenomenon of shortwave infrared moving readily through glass and long-wave infrared being reflected. Now you can see here that this low E coating is probably for a cold climate, right? Because I'm trying to keep the energy that comes in as electromagnetic wave inside the building. Where would I put the low E coating if I wanted to keep the energy out? Well, I'd put it here because it's really hot outside and cool inside. So the relationship between how I want to control or manage the heat transfer is going to be tuned to the climate of the building where the building is constructed. And it's why we're here. The greenhouse effect, very high energy, shortwave infrared, readily passes through the Earth's atmosphere. It heats the surface of the Earth. The surface of the Earth rises in temperature, but it can only generate long wave infrared, which the atmosphere reflects back. If we didn't have this phenomena on Earth, there would be no life. Now, if the atmosphere changes enough to keep too much of the long wave infrared energy in, we get the greenhouse effect, we get climate change. And so the science behind how heat transfer works is important at a detail level of the building for the glazing, but for the whole planet, it's just as important, but it's exactly the same physics. So how do we measure heat transfer? And, you know, since this is just a fundamental course, we're just going to look at the three basic units we have to do for radiation, conduction, and convection. And, sadly, we use a incredibly archaic, almost random system for measuring heat transfer. It's the British thermal unit. It's so archaic that the Brits don't even use them anymore. But our basic unit is the British thermal unit, the BTU. What is a BTU? The BTU is the amount of energy it takes to raise a pound of water 1 degree Fahrenheit. So a pound of water is a pint of water, and 1 BTU, which is about the same as a kitchen match, would raise the temperature of that water 1 degree Fahrenheit. Nobody uses BTU, nobody uses pounds of water, nobody uses Fahrenheit. Only we do, because we're special. The key thing is a BTU is really, really tiny, right? And that's going to come back as important later in Unit 2 on Thursday. When we talk about radiation, how many BTUs are we talking about? Well, direct sunlight is about 500 BTUs per square foot. So this is just a reference point. The BTUs are small, but if there's a square foot and there's direct sunlight, say, hitting that glass or hitting the surface, it is moving 500 BTUs per square foot through radiant heat transfer. Conduction. If I have 1 inch of fiberglass insulation, it allows 0.3 BTUs per square foot per hour at a 1 degree temperature difference. This is the basic unit of conductive heat transfer. We're going to come back when we talk about insulation. But the key thing is it's a rate, right? We've got BTUs per square foot per hour. So that's important that when we think about how conductive heat transfer, we're looking, as a rate. Finally, convection. Air carries about 1/50th of a BTU per cubic foot per 1 degree Fahrenheit. Whoa, wait a minute. Why in the world would we choose to move heat either in one direction or the other using air? It's pitiful. Air is so not dense that we can't rely upon it to carry much energy at all. However, air is attractive because we can heat and cool, and if it leaks a bit, we don't care. If we were doing heat transfer with a liquid, whoa, all of a sudden the number of BTUs you could move per cubic foot of the material would skyrocket, right? But water can leak with grave consequences. So when we talk about how heat transfers in buildings, we're always looking at both the science behind it, but the practicality as well. But we've picked some strange units. We've picked some strange ways to go about creating thermal comfort in our buildings. So just a quick note, radiation, when we talk about heat transfer, it's BTUs per square foot. For conduction, it's BTUs per square foot per hour at 1 degree temperature difference. And with convection, we're talking about cubic volume because we've moved on to fluids, liquids, and gases. One of the things we have to be really careful about when we talk about high performance, I didn't include this in the definition at the very beginning when we talk about better homes, but it would do very little good if we had really high performance energy efficient buildings and people weren't thermally comfortable. And designing, specifying, and constructing buildings for thermal comfort is not necessarily the same thing as doing those 3 activities for energy efficiency. So when we talk about making buildings work better, we don't want to do that sacrificing thermal comfort. So I'm going to take a couple minutes here to just talk very quickly about thermal comfort, but it'll come back to be important in all of our work. So there are 4 environmental factors that affect how comfortable people are. The mean radiant temperature, we're going to come back to that briefly in a second, air temperature, airspeed, and relative humidity. And these are in decreasing broadly in levels of impact or importance. There are two personal factors that affect thermal comfort: what the activity level is of the person in the space and how much clothing they have on. But by far, thermal comfort is dominated by something called operative temperature. So, mean radiant temperature. This fella is standing in a room, and all the surfaces he faces or that he can communicate with are different than his temperature. The surface of his core is about 85 degrees. The surface of his exposed hand and face is 90. And so wherever these temperatures are higher than this temperature, he's losing energy. And wherever a temperature is higher than his body temperature, the net transfer is to his body. But we call the mean radiant temperature if we average together all of these temperatures based on how large the surface area is and what the temperature is, we would be able to calculate the mean radiant temperature of the room. And operative temperature means that like 90% of a person's thermal comfort is whatever the mean radiant temperature is. How are all the surfaces exchanging temperature through radiation with this individual? And the other half comes from the air temperature. So we take those two temperatures, add them together and divide by 2, and that's the operative temperature. This becomes really important because while you do get impact from the moisture content of the air and airspeed, the two that really drive thermal comfort are the mean radiant temperature and the air temperature, and they contribute equally to thermal comfort. That principle of physical science is going to be very important in terms of how we keep people comfortable. All right, so take a deep breath because we just got done how heat gets around. Now we have to talk about how water gets around. And it's, let's see, it's, we have about what, a half an hour left?
Yeah, just about.
Okay, so we're going to go pretty fast. I know you may have questions, but we're going to have to rock it through here. All right, so how does water get around? Here's the first sad thing. Thinking back to when you took physical science in the 9th grade, there were 3 states of matter: solid, liquid, and gas. Turns out that since we all went to high school, we discovered that there is something called films. Films are when you have porous materials and the molecules hang out around those pores, and they don't act completely like a liquid and they don't act completely like a gas. It's called film movement, and it's called desorption and adsorption. You think, oh, okay, so another state of matter. Why do I care about that? Well, notice it's important when you have porous materials. Well, how many materials we know, keep that in mind. We're going to come back to that in a second when we talk about how water moves through building materials. But when we talk about moisture transfer, there are 4 types of moisture transfer. And the very first is just bulk liquid water. And these are sort of in order of importance in terms of management. Because bulk water management involves so much water, it's going to be at the top of our list for managing moisture in buildings. But we all know that, you know, bulk water is ruled by gravity, mostly. The second way that water can move around as a liquid is through wicking. This is a 9th grade experiment. These are different tubes of different diameter suspended over water that's been dyed, and how much that water climbs up the level of the tube. Look, it's exponential, right? You make that tube really, really narrow, and the water climbs against the force of gravity, all by capillary action or wicking. And it has to do with how strong water is attracted to other materials and to itself. So this is a really good thing for trees, right? Because it means they can lift water large distances for free. It's not terribly good news for buildings. So when do materials wick? Well, it's when they're porous. So now we have liquid water We have liquid water coming down that we have to worry about. Now we have liquid water going up that we have to worry about if we have porous materials. Well, what do we have here? Brick and mortar. They're both porous. Cellulose insulation, fiberglass insulation, porous. We can get wicking. Gypsum wallboard and wood, porous. We can get wicking. And in this last example, we have concrete, which is porous. And what's this layer right here? Well, everybody knows what that is. That's sill seal, right? We put the sill seal between the slab and the floor here. This is a slab on grade home. Well, that's to stop the air leakage. Well, it turns out that this sill sealer is closed cell spray foam or closed cell foam. Closed cell foam is non-porous. Not only is this sill sealer here a air seal, it's a capillary break. So if we want to stop the flow of water in buildings, we have to create a capillary break. We'll come back to that in part 2. The third way that moisture can move around is by leaking air. And so the first 2 forms of wetting were liquid water. Now there's going to be 2 types of moisture movement that we have to worry about, that is water as a vapor. And so how do I know that this is leaking air? I know that because of the pattern of the mold. So something that's going to come up quite often is that when we're evaluating heat transfer and moisture transfer, it's the patterns that are going to be important in terms of learning how to overcome uncontrolled heat transfer and moisture transfer. This is a building in, this is about 30 miles from the Canadian border. I got called in because this is a very high performance home. It was incredibly airtight. Sure looks like a water leak up at the roof level, doesn't it? This a big puddle on the ground. Turns out this is an air leak. The warm, moist air is leaking out the top of the building during the winter, but when it gets cold enough, it condenses. And what's crazy about this is that the escaping air moves according to the rules of vapor and air transfer, but when it condenses to liquid, now it's going to be ruled by gravity or wicking. So it gets tricky when we have uncontrolled moisture movement and we have them moving from the liquid phase to the vapor phase and then back again. So this whole issue of condensing surfaces becomes really important, even sometimes in milder climates, but certainly when it gets pretty cold or when it gets pretty warm. So we can talk a little bit about tools, but understanding dew point or condensing temperature is important. You can go and get for free this app called SciCalc, and it tells you what you can do as inputs and outputs. And you can see here that you can type in the dry bulb temperature, that's dB, and the relative humidity, RH. And as soon as you put those inputs in, one of the outputs is 50 degrees, 50.5 degrees Fahrenheit dew point. That is the same as 54.7 grains of water per pound of dry air. Whoa. And that's equal to 0.37 inches of mercury vapor pressure. Okay, I don't know how helpful that is. We have to come back to that as well. But the relationship between the air temperature and the relative humidity content is critical in understanding when vapor will condense and turn from a vapor problem into a liquid problem. The last form of heat transfer we have to worry about is straight diffusion. If the concentration of water molecules here is greater than here, we get flow. So it's high to low. It's higher concentration to lower concentration. It's higher vapor pressure to lower vapor pressure. And it's a push. It's a pressure. How do we measure that pressure? Well, you'll hear people talk all the time about what's the perm rating of that building material. So the perm rating is based on a unit of measurement called the perm. What is a perm? We know that it's a way that we can understand how water as a gas moves through building materials, but what is it actually equal to? 1 perm is a grain of water moving through 1 square foot of building material in 1 hour at 1 inch pressure of mercury difference. Okay, so there's 2 units here that I understand, square feet and hours. What the hell is a grain of water? And what's 1 inch of mercury pressure? It turns out there are 7,000 grains of water in 1 pound of water, which means 1 tiny drop of water is about 1 grain of water. So I'm not talking about an eyedropper. I'm talking about like a micro pipette. If I take a really, really tiny glass cylinder and I pick up 1 drop and I let it drop out, if you did that 7,000 times, you'd fill a pint. 1 inch of mercury is about the vapor pressure difference between the inside and outside of a refrigerator inside a greenhouse. Crazy British thermal units, like crazy vapor units. Where do these come from? Why do we use them? I wrote a blog about this that you might want to read on Green Building Advisor. We don't have time to go into it here, but there's a very interesting reason why we ended up with these units. What does it mean to us? It's small. So the only redeeming thing about all this is the way we measure heat movement is with a really tiny unit called a British thermal unit. The way that we measure how vapor moves through building materials, the perm, also a very, very tiny unit. And what it means is that by diffusion, vapor moves very, very slowly. And here's the most interesting thing about this. Getting assemblies wet by diffusion is usually slow and not a big problem. We're not worried about vapor moving by diffusion in terms of creating moisture problems, generally. But once an assembly gets wet, once the moisture gets inside a building, how does it get out? Can I drain it? No, I can't wick it. No, I can't like put a blow dryer into the wall and dry it out. Once water gets into our building assemblies, the only way it gets out is by diffusion. So when we talk about the vapor permeability of building materials, it's not because we should be protecting them from getting wet by diffusion. It's that if they get wet, we have to understand the permeability of building materials because that's how they're going to dry out. So this relatively simple physics, biology, and chemistry is going to come back all day long in part 2 on Thursday. How do we translate this into what the heck should I be worried about when I'm designing, speccing, and constructing buildings? So here are some representative perm ratings. Drywall is 40 perms. What does that mean? It means in 1 hour per square foot per mercury pressure difference of 1 inch, 40 perms or 40 grains of water will move through that drywall. Cellulose is 75 perms. Latex paint is 3 to 5 perms. Plywood is 2 to 15 perms. 1 inch of blue board is 1 to 2. Craft paper has a variability. All these numbers are going to be important, not in terms of how we protect buildings from getting wet by diffusion, but how the building dries out should it get wet by any of the other means of moisture movement. And of course, plastic sheet like polyethylene, incredibly low vapor permeability. Now, one last thing when we're talking about what we need to understand about heat and moisture, and it's those pesky occupants. Joe Stiebrick is the guy that I learned building science from. And one of the first presentations I saw him do, he said, hey, look, I'm an engineer. If we could keep people in windows out of buildings, they'd work exactly the way we want them to. Both his wife and his daughter are an architect, drives him absolutely crazy. So when we talk about sources of water coming from occupants, we make this high performance building, we turn it over to the occupants or the owners, and we give them absolutely no way of measuring moisture in their buildings, either in the building materials or in the atmosphere inside the building. And then we don't tell them about how important what they're going to do inside the building is important in terms of moisture management. So just looking at this, what are the things that jump out at you? My wife comes down, I'm in the basement, I'm standing on a bathroom scale with a load of laundry. And she said, I worry about you, Peter, but I know you don't have a girlfriend and you're not an alcoholic. What you do in the basement with your wingnut hat on is all up to you. So what was I doing? I was weighing the laundry. I was trying to figure out, well, how much moisture is there in a load of laundry? Turns out that it's about 4 pounds per load for a horizontal axis washer. If you have a top loader, because it doesn't spin as well, 8 pounds, twice as much moisture. You hang all those clothes in your basement. What have you done to the moisture management of your building? I don't know. Look at cooking. 1.2 comes off the boiling pot. More comes from the combustion of the gas. If you're burning propane or methane, there's only 3 byproducts of burning something. It's heat, carbon dioxide, and water. So every 90,000 BTUs is a therm. That's a gallon of water. You burn that inside your house, you've just dumped a gallon of water inside your house. So these are important for us to know in a high performance building, maybe, because we got to manage moisture better if we're going to manage energy better. But look at these two here. When people see this list, why are there building materials on here? What does that mean? And what's your guess for showering? Look at these other numbers. What would your guess be? It's surprisingly low. That's weird. I would have thought that the water generated by a shower, a 5-minute shower, would be higher based upon these numbers. The reason it's higher is because we see it, or we think it should be higher. We have a closed small room, lots of hard, non-porous, cold surfaces, and we put a bunch of vapor in there. And what does it do? It condenses. When we see moisture, we worry about it. When we don't see it, we don't worry about it. So it's a surprisingly small amount of moisture, but we micromanage it because we can see it. This is really important when we talk about what we have to do in high performance buildings to sensitize people to how energy moves through their building and how moisture moves through their building. And then the other really surprising thing here is how much moisture comes out of the materials we're using. A 1,000 square foot 4-inch slab of concrete in the first 6 months gives off 1,000 pounds of water. That's 125 gallons of water. Now, if you're building slowly and you allow that moisture to go out, who cares? But if you accelerate or condense the construction process, you could now be dealing in a high performance building with a one-time load called the moisture of construction that could really be a problem in your building. So I think you can see where I'm headed here. Basic science, biology, chemistry, and physics is really, really important in high performance buildings. And we have to understand them better if we're going to make them better buildings for their occupants. All right, so here's the summary. I'm just at about time for the whole unit. So let's do a real quick summary of what we've covered today. We only have to keep track of 3 forms of heat transfer, and radiation, conduction, and convection. And the way they work is incredibly different and constantly changing. So when we're trying to assess the energy performance of a building, we're going to have to look at how the building enclosure and the mechanical systems manage the 3 forms of heat transfer. Sadly, moisture moves in 4 ways instead of 3. And when we worry about water, we basically are going to end up worrying in this order. If we can't manage bulk water, it won't matter what we do down here. If we can't manage wicking or capillary movement of water, these 2 don't matter. And then air transported moisture can become important when we talk about condensing surfaces. And the final point here is that very few buildings get into trouble because of vapor moving by diffusion. However, once the building gets wet by one of these other more serious forms of heat, moisture transfer, we're going to have to rely upon this very weak cousin to get that moisture out. And we'll talk more about how important it is next time. They both always move from high to low and warm to cold. And they do that at the speed of light for radiation, pretty quick for conduction, and quite slowly for convection. We still have to manage all of them. And then again, the list above is by priority, and often this list for moisture is important in terms of amounts. And what's going to be bedeviling is that climate, daily cycles, occupant schedules are going to complicate both the way that heat moves through buildings and the way that moisture moves through buildings. So the third thing in terms of covering the basics is we've learned about heat and moisture transfer. How are the two related? And so that's really what I want you to think about between now and Thursday. And here's your homework. So come back to class 2 with one of the following for class discussion. If you can take a picture, or you can do a quick hand drawing, or you can send a report, I would encourage you to do that. I'm going to give you my email, and we will discuss your homework based upon how seriously you took the homework exercise. So if you send me a drawing or a report or a photo of the principle that's being expressed, then you're more likely to have that rise to the top of what we talk about at the beginning of the session on Thursday. So find a physical, chemical, or biological example or expression of building performance that you don't understand. Like I went home, I tried to figure out how heat and moisture move through buildings, and here's a way that one of those things is happening and I don't understand it. Or in your work, look at a design materials or construction process or an element of that process that deals with how heat and moisture moves through buildings. Pick one that you don't understand and bring it to class. The idea here is that when I was working for Joe Prue and had a master's degree in something, and I had taught biology, chemistry, and physics, I didn't interpret them or apply them to the way that buildings work. It's sad. I had to be dragged kicking and screaming by the NHB Research Center and by Building Science Corporation to understand that the way that buildings work is all about the physics, the chemistry, and the biology as it plays out in buildings. Or come back to class with a description of a situation that requires a custom site-specific or climate-specific science-based performance solution. So this exercise is about science and buildings. This exercise is about science in buildings. And so you can see what I'm leading to here. What we're going to be doing on Thursday is taking the building science and tuning it for site, tuning it for climate, and tuning it for the relationship between how the building enclosure performs with the mechanical systems. Because that's going to be all about electrification of buildings, how the mechanical systems relate to the performance of the enclosure, and that's how we get truly high performance buildings. And with that, I can turn it back over to you, Ian.
Awesome. Yeah, thank you, Peter. That was excellent. Just connecting so many scientific concepts and terms that I haven't thought about in years, but often go overlooked, you know?
It's fun stuff.
Yeah, clear as day the way we put it here, which is awesome. And definitely teed up well for number 2 on Thursday. I will share the presentation and just some of the links that we reviewed today over email probably just informally via my direct email today, and then a more formal follow-up after Thursday, including opportunities for you all to share your feedback and get more involved with the High Performance Fundamentals series.
Ian, sorry.
Yep.
My email, if you want to send me a photo or a report or a hand drawing, peter@building-wright.com. There's a dash between building and right, and right is with a W, W-R-I-G-H-T.
Okay. Let's see, Peter, I'm just gonna add that in the chat.
Perfect.
Building-Wright.com.
Yep, and there's a dash between the end of building and the beginning of right.
Gotcha.
Because some guy in Australia took the one without it.
Yeah, so we had AIA Health, Safety, and Welfare units available for today. In registration, you should have been prompted to include your AIA number. If not, you're welcome to reach out to me directly and we can get you all situated there. Slides recording survey coming to you soon, formally on Thursday. But we'll get some information out to you this afternoon to help you finish the homework assignments. And then, so just upcoming High Performance Fundamentals courses. We have session 2 on Thursday. The Zoom link for today is good for Thursday. So ideally it showed up on your calendar as both Tuesday and Thursday when you saved it to your calendar. I will include the Zoom link in my email this afternoon just to clear anything up if there's confusion there. But we would love to see all of you attend Thursday as well, just to follow up on that homework and really apply these concepts and terms to building as a system. So that's part 2 on Thursday. And then end of June, we have the Introduction to High Performance Buildings and Career with Rick Chitwood. That is on the 21st of June. And then High Performance Enclosures in July. These are the first 3 of the series, and registration is live on the website. So 3cren.org. Please visit the website to register. And then the following 3 of the series we will roll out through August, and registration will follow. Regularly scheduled program. If you're interested, next week we have Home Performance Tools of the Trade. Beginning of June, all electric construction, focus on heat pump water heaters. And then the following day, Healthy Homes for a Healthier Living, focused on indoor conditions. A lot of the terms and concepts that we've gone over today and kind of applying them, but at a more high level household focused event. So yeah, just a few things for your calendar there. With that, I think, next slide is just contact information, but I know we do have a few minutes to answer any questions that may come up for Peter, and you're welcome to do that now. So if there are any questions, we'll take them now. If not, we will see you on Thursday, but definitely giving you an opportunity here.
So when you don't get any questions, you've either done an incredible job or you need to go back to the drawing board.
I'm looking forward to reviewing the PowerPoint and just trying to, directly go through what we did today to apply that to the homework, which will be exciting to hear from folks on Thursday. But yeah, going once, going twice. If not, we can follow up via email and close it out for today.
Well, I look forward to hearing from folks between now and Thursday, or if not, we'll see you same time 2 days hence.
Thanks so much, Peter and Ian. Have a good one.
Thanks much.
Thank you, Ann.
Working with you guys.
Of course. Thank you, Peter. We'll see you soon.
All righty. Take care, everyone.
Bye.